The new Quad SPI flash format, which uses a modified 6-pin SPI configuration, is much faster than traditional SPI formats. Quad SPI delivers a transfer rate of 40 megabytes per second, the same as using two 16-bit parallel devices. Using Quad SPI is often much less expensive than the parallel approach too, since it uses far fewer pins and a much smaller package. It would seem that Quad SPI flash would be a good replacement for parallel flash in embedded systems. But the reality is that today's 32-bit microcontrollers aren't typically designed to support Quad SPI flash at its maximum speeds. But now that NXP has the patent-pending SPIFI peripheral, Quad SPI flash can be used by LPC ARM microcontrollers and takes advantage of the many benefits of Quad SPI flash. The patent-pending SPIFI peripheral lets low-cost SPI and new Quad SPI flash memories be connected directly to the memory map of an ARM Cortex-M3 microcontroller. So the MCU can use external SPI flash with only a minimal performance penalty compared to external parallel flash memories. The microcontroller can access the external flash memory directly, without a software API or library. When used with a Quad SPI flash, for example, the SPIFI peripheral supports a data transfer rate of up to 40 megabytes per second. The designer can choose a less expensive SPI flash device, with its compact footprint and simple configuration, but doesn't have to sacrifice on performance. The designer may also be able to choose a smaller, less costly microcontroller, because the system won't need a bulky interface for external parallel memory. The SPIFI peripheral enables an embedded system that makes better use of memory resources, yet remains compact and efficient while lowering overall cost. The SPIFI peripheral is a dedicated function that will initially be available on the NXP LPC 1800 series of ARM Cortex-M3 microcontrollers. It will also be available on upcoming product lines, including the LPC 177X and LPC 178X, and the Cortex-M4 series of digital serial controllers, or DSCs. SPIFI supports most serial flash devices on the market today, including those with quad read-write capability, and is designed for easy configuration and programming. It uses 4 or 6 pins, depending on the type of serial flash used, works with a small register set, is optimized for efficient memory transactions, and uses software commands that reduce CPU overhead and streamline memory interactions. SPIFI is compatible with both standard and the new Quad SPI flash format. SPIFI has been tested and validated with a variety of SPI and Quad SPI flash devices from all of the leading suppliers. Embedded applications that use a 32-bit microcontroller are increasingly tasked with offering a range of sophisticated features for managing multimedia, photos, and other data-intensive content. This is particularly true of systems that present a human interface, since today's users have come to expect a graphical display that lets them interact with window boxes, photos, animations, sound files, and more. Also, as products become increasingly international, they have to operate in different languages and may need to support several sets of alphabets and non-Roman characters. All these requirements place extra demands on the system's memory resources. Most 32-bit microcontrollers are equipped with a certain amount of on-chip flash memory that can be used to support data-intensive features, but it's often not enough to support the entire application. The on-chip flash is typically limited to 1 megabyte or less. That may be enough to house the bulk of the critical application code, but it may fall short when it comes to storing all the other things the application needs, such as lookup tables, images, photos, sound files, multiple languages, and so on. For these items, designers often turn to external flash memory because it is significantly cheaper than on-chip flash and is readily available in sizes in excess of 8 megabytes. Embedded designers typically use three main types of memories: on-chip flash, parallel flash, and serial flash. On-chip flash, ranging from as little as 8 kilobytes to as much as 1 megabyte on LPC ARM microcontrollers, is the fastest and most secure solution. But since it is built on a microcontroller fab process, it is the most expensive of the three options. Parallel flash, typically offered in 8-bit and 16-bit data options, is fast, although not as fast as on-chip flash. However, it is only available in larger packages, uses a lot of pins of the microcontroller to interface to it, and is relatively expensive. Serial flash, the lowest cost of the three options, comes in small packages and uses only a few pins of the MCU. But serial flash, when connected via a standard peripheral interface or SPI, is very slow. SPIFI with Quad SPI Flash offers the performance of parallel flash with the low cost and small packages of serial flash. This graph assumes that the typical parallel flash access time is 90 nanoseconds with sequential reads. This equates to 11 megabytes per second throughput for 8-bit parallel flash and 22 megabytes per second for 16-bit parallel flash. Typically, there is no buffering in parallel nor flash, so the data rate is constant as the number of bytes per fetch increases. However, serial flash supports buffering, also known as bursting, so it can buffer significant amounts of data. This buffering allows Quad SPI Flash to achieve throughput data rates of 40 megabytes per second at 80 megahertz, which is equivalent to running two 16-bit parallel flash chips at the same time. Prior to the introduction of SPIFI, in order for the CPU to use data from external serial flash, first the CPU needs to write to the control register, then the data needs to be loaded into the buffer, which, when complete, updates the control register. The CPU then reads the control register and transfers the data from the buffers into the CPU RAM. All transfers have to go through a buffer in the interface and then be transferred to RAM. Sometimes the transfer is done via DMA, which is more efficient, but the CPU still needs to read the data from RAM. This traditional process of using serial flash is complicated and slow. With SPIFI, the external serial flash appears in the memory map and is fully visible to the ARM core. So the external memory can be managed by the CPU in the exact same manner as internal flash. The data does not have to be transferred into RAM. The SPIFI peripheral is connected to the microcontroller's Application High-Speed Bus, or AHB, which is used by the processor core and the on-chip memories. The CS pin is the chip select for the external flash memory. If more than one serial flash device is connected to the MCU, the chip select will be used in conjunction with general-purpose IOs. The IO2 and IO3 pins are only used if the external serial memory is a quad type. A compact register set gives the SPIFI peripheral a considerable amount of intelligence while keeping it simple to use. It takes just 8 registers to control the SPIFI function, interface with the external SPI memory, store and retrieve data, and monitor operation. Since the built-in ROM API handles setup, programming, and erasure, handling the external SPI memory in an application is only a matter of a few API calls. As a result, the SPIFI peripheral is simple to configure and easy to support in the application. The API also automatically detects which Quad SPI Flash device is connected by reading its JEDEC number and configuring SPIFI to optimize performance of the external serial flash. The external memory responds to commands sent by the microcontroller software and to commands automatically sent by the SPIFI peripheral when its software reads the serial flash region of the memory map. Commands are divided into fields called opcode, address, intermediate, and data. The address, intermediate, and data fields are optional, depending on the opcode. Data fields are further divided into input and output data fields, depending on the opcode. All commands to the external SPI memory can be handled by calls to the ROM API. The SPIFI ROM API driver lets the contents of the external SPI memory be accessed using simple load commands, so the application code remains simple and easy to write. LPC ARM microcontrollers with the SPIFI interface have two options for booting with the external SPI flash. First, a user may set certain external pins low, which tells the MCU during startup to look for external SPI flash connected to SPIFI. But if a customer wants to use those boot pins for other functions, there is an option to set a flash bit to override the pin setting. This will free up the pins and let the user not worry about the dual functionality of the pins. The SPIFI software supports write while execute functionality, which means it can program or erase the external memory simply and quickly, even when the processor is executing code from on-chip flash. Since the SPIFI peripheral can run on its own without interaction from the CPU, the system can perform its functions without interruption while the serial flash is being reprogrammed. This feature can be used to perform software upgrades in the field, because the system can write to the external memory without interrupting critical application code. The golden copy of the application code can be kept in on-chip flash, while the code updates are loaded into the external SPI flash. Even if there is a power failure or other flash update interruption, the on-chip flash remains uncorrupted, and the software updates can be written again into the external SPI flash. Typically, Quad SPI flash is 33 to 60% cheaper than parallel flash. Additionally, Quad SPI packages are 8 or 16 pin, while parallel flash is in 48-pin packages. The smaller pin count packages save system cost in two ways. The reduced number of external pins reduces assembly costs and simplifies printed circuit board routing. Furthermore, the smaller, lower pin count packages occupy less printed circuit board area, which allows for smaller overall products. Finally, the LPC ARM microcontroller package can be reduced by using SPIFI instead of parallel flash. The SPIFI interface only requires 6 pins of the MCU to be connected to external flash. Parallel flash, on the other hand, requires 8 to 16 data pins, up to 25 address pins, and a chip select pin of the microcontroller just to interface to the parallel flash. By using SPIFI, the microcontroller can also be in a smaller package, saving assembly, PCB, and component costs while reducing EMI.